Okay. Now, last time we talked about the trajectory equation, d theta dr. In order to find the trajectory, we need to perform the integration. We integrate this equation to obtain the r as a function of theta, or theta as a function of r. Okay. As pointed out by this exercise, this integral can be done analytically if the potential energy is of the form UR proportional to R to the power 2 minus 1 or minus 2. So here we try to perform the integration. Basically, we need to make a few changes of variables, and finally, this integral can be recognized as a doable integral, and the answer is the arc cosine, right? And fixing the constants, we obtain the equation of the conic section. So this is the equation of conic section. On the other hand, we can also go back to this equation 30 or equation 31, right? If we have equation 30 and we have the inverse square law, so F1 over U is actually proportional to R square, right? Proportional R square, U square, sorry, proportional U square. And U square divided by U square gives you 1. So the right hand side here is constant. So what you need to do is to solve this equation. U double prime plus U equal to a constant. Do you know how to do it? So there are two ways to do it. First, if you know how to do the integral after a series of changing of variables, you can figure out that the integral gives you the arc cosine as the final answer. On the other hand, if you don't want to do the integral, you can come back to this equation 30 or equation 31, as you like. And the inverse square law tells you that the right hand side of this equation is equal to constant, or the right hand side of this equation 30 is a constant. Okay, so we have a second order differential equations. To solve this second order differential equations is not difficult. We look at the homogeneous equation first. That means we set the right hand side equal to 0. Then we have something very much like the simple harmonic oscillator, right? Then the solution of the homogeneous solution will be a linear combination of cosine and sine theta, cosine theta and sine theta. Or we can write down as the solution can be written as a cosine theta plus beta. Beta is an arbitrary constant. A is an arbitrary constant. So this is the homogeneous solution. For particular solution, it's also very simple. This is constant. So we can set the particular solution to be this constant, all right? So a combination of cosine function and a constant. Can you follow me? Okay, the homogeneous solution, the constant disappeared, is a harmonic oscillator, all right? Particular solution, very simple. We want to take this away. If U is a constant, then it fits the equation. All right, then combine them, you have a solution containing cosine function plus a phase vector and also this constant term. All right, then you try to group them together, then you get the usual conic section trajectory. So there are two ways to do it. So then you may ask, what happened to let's see. Say for n equal to -1, we can do it two ways. Solving the integral, doing the integration, okay? So solving the second order differential equations or performing the integral. Now for n equal to 2, n equal to -2, you can also try both ways. All right, but this time the equation is no longer so simple. On the right hand side, it is not a constant anymore. It will be 1 over, it is an explicit function of r or u. So you have to solve this second order differential equation smartly. On the other hand, performing the integral needs a clever change of variables. Okay. So I leave it to you to pursue further. Okay. All right. Then we continue our discussion of the central force motion. We'll concentrate on Kepler's laws in this lecture. Now, Kepler's laws are very famous phenomenological laws. What does it mean? Those three laws are not derived or deduced from some higher principles. All right. They are derived from a set of data, a large set of data. All right, as pointed out here, Johannes Kepler was the assistant of the 16th century Danish astronomer Tycho Brahe. The teacher is a very, very careful and hardworking astronomer. He made a lot of planetary measurements very accurately. Okay, I wonder, when I was a student, I wonder how Tycho Brahe could spend so much time on doing the observations without advanced instruments. Okay, so he might have a pretty good telescope, but at that time, no computerized data collecting. So he had to write down or record. He had to record all the data by himself, one by one, spending nights almost every night to get such a huge set of data. Perhaps it is fun. Okay. For now, in Hong Kong, I don't think you can do the same thing because of the light pollution. On the other hand, Tycho Brahe had a very smart student, Kepler, who is very good at mathematics and also very persistent. So he Kepler looked at the huge set of data and tried to fit the data to some equations, some mathematical expressions, some functions, all right? And it took Kepler 18 years of laborious calculations to obtain the 3 basic laws. Do you think you'll be persistent enough to work on that project? If you got paid. Okay. So basically, you won't get paid. Am I right? Because you spent 18 years on a project. But actually, I think at that time it is it is not. It does not emphasize on the number of publications published every year, right? So if we can go back in time, and we may be able to follow suit. All right. But it is amazing that if you have such a huge of data and you don't have computer, and you try to fit it with a function, how can you do it? Have you ever thought about that? You don't have a computer. You don't have a calculator. So remember that you don't have a computer. So plotting is not easy. Am I right? Plotting is not easy. Plotting curves are not easy at all. So it is really amazing. It is really amazing. All right. So the first law tells us that each planet moves in an ellipse with the sun at one focus. Elliptic orbits are characteristic of the inverse square gravitational force. The second law, the radius vector from the sun to a planet sweeps out equal areas in equal times. Now, the first law seems to be okay if you just keep connecting the data for each planet motion, right? So, well, roughly it is a ellipse. So that conclusion is okay. But the second law is not that simple. You can realize that the radius vector from the sun to the planet sweeps out equal area in equal times. Wow, I mean, it's difficult to realize this by looking at the huge set of data. You have to be very patient, very persistent. Now, to show that this is correct, or to derive this as Kepler's second law, we start with the gravitational potential UR, which is an inverse square law, all right, which obeys this, the gravitational force obeys the inverse square law, and the gravitational potential is independent of theta. The canonical momentum, i.e. the angular momentum, is conserved. So we have here the angular momentum is equal to mu r square theta dot. Now we rewrite this expression in this form. All right, in this form. So we have dt equal to mu divided by L time R squared times d theta. All right. Realizing that, or recalling that the infinitesimal area swept by this radius vector is equal to 1/2 R squared d theta. All right. I expect that all of you know this for circle for an arc. All right. So this is 1/2 R squared d theta. So this expression on the right hand side, it can be rewritten as this. So the dt is proportional to the infinitesimal area swept by the radius vector. All right. So integrating this expression on both sides to a finite time. On the left-hand side, you have the time duration for the journey. On the right-hand side, it gives you the area covered by that radius vector during that period, during that duration, right? So this, we can see easily that, yes, as long as delta t is the same, then the delta A will be the same. All right, so the radius vector from the sun to a planet sweeps out equal areas in equal time. All right. Now the third law, the period of revolution of a planet about the sun is related to the major axis of the ellipse according to equation 5. Okay, where k is the same for all the planets. Wow, this is really, when I was in high school, I found that this is really amazing. Why? This exponent, 3/2. Am I right? 3/2. So he must somehow realize that he have to write down all the period data, the data on period. Okay, first write down the data on period and then square it. Then you have the square of the period. On the right hand side, he has the data on the area and then raise it to power 3. And they compare. And there is a common ratio. This is not simple. This is not simple. Keep in mind that he does not have computer. He does not have calculator. Okay? The first difficulty, the first hurdle is that he must realize that this is true. I mean, he has to take the square of the data of the period, and also take the cube. Okay, raise the data of the area to the power 3. This is not simple. This is not simple. Okay. Instead of going through this trick, maybe we can just go to here. Look at the exercise first. Now, we know that the total energy is conserved, and the total energy is given by this expression: radiokinetic energy, the centrifugal potential energy, the gravitational potential energy. All right. So we move this R dot square to the left-hand side and move the E, the total energy constant, to the right-hand side. All right. R dot is equal to dr dt. Then that means the whole expression can be separable. So we have dt on the left-hand side and dr, and also the integrand given here, which is a function of r only on the right-hand side. If we integrate both sides, so we start from T naught to T final, okay? That means we integrate from the initial position to the final position. A simple choice of the limits is obviously as follows. The lower limit, the shortest distance from one of the focus. The upper limit, the longest distance from that focus as well, right? Then after the integration, then you will get half period. Am I right? Half period. Now what you need to do is to do this integration. Do you know how to do it? Okay, 5 minutes. Performing the integral is the most straightforward approach. Now, without the variable r in the denominator, in the numerator, the integral can be done immediately. Am I right? Just like what we have gone through before. But now we have the extra r. So how can we get rid of it? So you perform completing square, right? Just like what we have done for the orbit. But then how are we going to take care of this r here? This one. Completing square. Mm-hmm. Right. So you turn it upside down. The whole thing as use let's say some variable square. Mm-hmm. Okay, try it. It seems that so far we have to do a lot of integrals. Can mathematical help? I think don't worry. You have a good chance to work it out in your homework. Okay. Now we'll try to go through it through the trick.
Okay. Let's do it together using the small trick.
So this is the third law. Can you hear me? How about from the device? Can you also hear it from the device?
Okay, let me just turn it on. Okay. I don't want to have echoes. That's why I sit here.
Okay. Now, so we try to prove equation 5. The period is proportional to the area, the 3/2 power of the area. So we start from the angular momentum first. All right. That is in equation 6. We try to integrate equation 6 to form a simple integration. So integrate from 0 to 1 period. On the left hand side, we have this. On the right hand side, obviously it is the area of the ellipse. By definition, the area of the ellipse is pi times AB. What is A and B? A, the semi-major axis. B, the semi-minor axis. Okay? Semi-major axis and semi-minor axis. Sorry, this is not the area. That is the the major axis. Sorry, I made a mistake. This is the major axis. Okay? Semi-major axis is A equal to A divided by 2. B is the semi-minor axis. Okay? So we move on. Conic section equation. We have derived the equation 8 and equation 9 already. Now, the semi-major axis, how can we find the semi-major axis? What we need to do is to add up the maximum radius, minimum radius of the trajectory, right? And divide it by 2. That means we want to find the position as theta equal to 0, and also the distance as theta equal to pi. Now, how do we represent the orbit? It is like this. So this is the origin. This is the radius, okay? And here is the center of the ellipse.
And this is the angle, theta. Okay? So R at theta equal to 0 is this distance. R at theta equal to pi is this distance. Add them together is the major axis. We take half, we get the semi-major axis. All right? So R at theta equal to 0, we have this. R at pi, theta equal to pi, we have this, according to this formula. So we combine them together and simplify. Finally, we have this. So it depends on the total energy and also the coupling of the force. Okay. So we find the semi-major axis. Then we want to find the semi-minor axis. How do we find it? First of all, we calculate the distance x naught. Okay. That is the semi-minor axis minus the R mean. From here to here, that is A. Okay. Let me erase it first. Here is the 0. This is the center. So here to here is A. Origin to here is our mean. Okay. So here to here is x naught. All right. That is the x naught. So what is x naught? We realize that our mean is equal to r at theta equal to 0. That means this one. And we know the A. A is this one. All right. A is this one. Then we combine these two terms. We have this. Okay. So this is x naught. All right. Get it? We move on. Now the semi-minor axis is given by this formula. Okay. Can you see it? That means if we come back to this diagram, at any angle, this is if this is x naught. This is our theta. Okay. Now cosine theta is equal to minus x naught divided by our theta. Can you see it? So basically, okay, let me. This is R theta. This is theta. Okay, semi-minor axis. This is the B, semi-minor axis. So B is equal to R square theta minus x naught square. And cosine theta is equal to minus x naught divided by R theta. Okay, get it? Minus x naught divided by R theta. Okay. So keep in mind that this is the origin. Our origin is at the focus on the right hand side. Then combining all these together, we have B equal to this alpha divided by square root 1 minus epsilon square. If we rewrite this in terms of A, the semi-major axis, then we have this. Okay, substituting the definition of the semi-major axis. Then we further simplify it. We realize that the semi-minor axis is actually depends on the angular momentum and also the total energy. The semi-major axis depends on the force constant and also the total energy. Okay. So we have A equal to minus K over 2E. B is equal to minus L square over 2 mu E overall square root. All right. Then we combine A and B together. So we have T equal to mu pi AB, mu pi A, and multiply the B. All right. And then making use of the definitions of capital A, the major axis. We know the semi-major axis, then the major axis can be done. We have this final answer. So we just plug back to the definitions in terms of A, All right. Then we get this very interesting factor, the major axis to the power 3/2. Now, if you are Kepler, if you were Kepler, are you satisfied with this expression? Why? Now, according to the third law, the capital T must be proportional to a to the power 3/2. It should apply to any planet. But actually, the proportionality constant is not a constant. Am I right? So if you have the data for Venus, if you have the data for Pluto, and you just try to figure out the proportionality constant, they may differ by this amount. The proportionality constant has some discrepancy, but is it significant? Yes, as pointed out here, even the largest planet and does not have a large discrepancy. So I think we have to. So if you consider Kepler's case, at that time he does not have a very accurate computer to help analyze the data. So to that extent, Kepler's conclusion is quite correct. Now the next topic we are going to discuss is the Laplace-Runge lens vector. Now so far we have discovered two constants of motion for Kepler's problem. The first one, conservation of angular momentum due to the rotational invariance or rotational symmetry. The second conservation constant of motion is the total energy due to the translation in time. All right. And here I'm trying to introduce you the third one, the Laplace-Runge lens vector. Now, can you guess the symmetry or the invariance associated with additional constant of motion? Can you guess what it is?
Can you guess? What kind of symmetry will lead to this constant motion? rotational symmetry gives you the conservation of angular momentum. Translation symmetry in time gives you the conservation of total energy or the Hamiltonian. Here, I tell you that there exists an additional constant motion for this particular problem, Kepler's problem, or for the inverse square law, for inverse square law. Say it again. Of course not. Why? It appears before the birth of special relativity. Okay? And it works for any inverse square law. Coulomb's potential, right? Coulomb's potential, inverse square law. So what do you think? Maybe. No. This is classical physics, very simple. No fancy things. We don't need 26 dimensions. Okay, let's go through it first. We consider the time derivative of this special vector P cross L, okay? Now remember that L is a constant motion, okay? Angular momentum is a constant motion. And here the P is the linear momentum. So P, remember that we confine the motion on a plane, on the XY plane, all right? So this is the linear momentum for the particle, reduced mass particle. Here is the angular momentum. It points in the Z hat direction. Okay, the rotational axis is the Z axis. If we take the time derivative of the linear momentum, we get this. dp dt give you the force, right? dp dt give you the force, i.e. minus du out dr in the direction of r hat. So when we differentiate this, the whole thing, we should have two terms. Am I right? We differentiate the momentum and also we differentiate the angular momentum. However, we know that the angular momentum is a constant motion. So we can just treat it as like a constant. And we plug in the definition, the results of equation 18, and also the definition of L, R cross P. Okay, get it? Okay, sorry. Does it work now? Sorry about it. Okay, I hope it works now. Okay, let me repeat a little bit. So we start with the P and L, and we take the cross product, and we look at this particular vector, all right? we take the time derivative of this vector. Since L is a constant motion, so we have only the time derivative of the linear momentum, and we substitute the results of 18 and also the definition of the angular momentum into this expression. We finally have this. Okay, we finally have this. This is our final results for the derivative. Now, be careful now. We have to do this slowly. Remember the triple product. This is the triple cross product. So it is equal to B vector times A dot C minus A dot B times C vector. All right, this is the triple cross product. Here we can easily see that we have a triple product. Okay, triple cross product. So we apply this formula to evaluate the right-hand side of equation 19. All right, R dot dr dt, the first term. The second term is R dot R. So we have R squared, okay? Remember that R vector dot dr vector dt is equal to R times R dot. Okay, equation 21. That is a key step. Then, making use of this key step, we can get the final answer here. All right, we can get the final answer here. Now, finally, we can factorizing the common factor R cube. So we pull out the R cube. That's what we get. Okay, pull out the R cube from both terms inside the square bracket. All right. Now, these two terms inside the square bracket actually comes from this one. Can you see it? Differentiating the quotient of two functions. All right. Okay, that's good. Now the U for inverse square law, we have UR equal to minus K over R. K is the constant, force constant. Then this equation 22 can be rewritten as this. Okay. Is it right? We move in the dur, dr. All right. And what is this? If I move this to the left-hand side, we have P cross L minus this term, mu K time R hat. Okay, mu K time R hat. Okay, then we get 0. And this whole term, we give it a name, Laplace-Rungelen's vector. All right. So this vector is conserved. Now this is this additional constant motion is unique for the inverse square law. And interestingly, inverse square law plays a very important part in classical physics, right? Gravitational force, electrostatic force, right? They are all inverse square law, okay? So if you go to, when we study E&M, electrostatics, you will realize that there is an additional constant motion, Rungelen's vector, okay? Now this kind of constant motion, we usually call it accidental symmetry. It is due to the accidental symmetry, all right? Here are some properties of the Rungelen's vector. This Rungelen's vector is perpendicular to L. Is it obvious? Perpendicular to L. If we take a dot product to L, the first term will vanish automatically. How about the second term? Is it 0? Why? Z is in the, L is in the Z direction. Am I right? Okay. So this is automatically, they are automatically perpendicular to each other. The projection of A onto the radius vector can be obtained as follows. A dot R, all right, what do we get? A dot R. This term is simple. Give you R, all right, proportion to R. How about this term? Is it 0? So what is it? Don't look at the notes. This is a triple product. It has a special property. P cross L dot R vector don't look at the notes yet. Right, you can have permutations, right? Cyclic permutations. You can always perform permutations. P cross L dot R. You can perform permutations. L squared, yes. because you can move the R inside, then you have R cross P dot L. Okay, so it's L squared. So the dot product gives you L squared minus mu K R. And you can write it in a nice form like this. 1 over R equal to mu K over L squared plus 1 plus A magnitude divided by mu K cosine theta. Okay. Now, we compare with the standard conic section trajectory. We realize that the eccentricity is actually equal to magnitude of the Runge-Length vector divided by mu K. How nice. So the Runge-Length vector is actually a parameter characterizing the eccentricity of the orbit. Okay, once you have a definite orbit, then it fixes the eccentricity, which in turn fixes the Runge-Length vector. All right, and we can rewrite this relation in this simple form. The magnitude square is equal to the total energy times L squared plus the mass, okay, mass square of the particle. We can always normalize the force constant to be 1. Can you follow me? We can always normalize the force constant to be 1. That means we can define the energy unit, right? Okay, so this is a very nice constant motion, and it is due to the accidental symmetry. All right, so far, any questions? Our next topic will be more challenging. Scattering orbits. Scattering orbits. All right. So we have to know, we have to introduce a number of new terms like the impact parameters, scattering cross sections, and all these. I think I'll wait until next week, next Tuesday, to finish that. So any questions about the Runge-Length vector and also the Kepler's 3 laws? Now this constant motion, the discovery of this constant motion is also interesting. It is not obvious at all. It is not obvious at all. It is not obvious. Okay, so if you don't have any more questions, I think I just stop here and continue next time.